So far we have used the variable t belonging to r and transformed it to the domain of omega, which is the angular frequency. Sometimes it's useful to express the angular frequency in terms of the usual frequency measured in hertz. It's just 2 pi times f, or some other times this is denoted by the letter nu. This is a Greek letter. Some other times, instead of using the variable t, we need the spatial variable. It can be labeled by x, we can also have y and z. Let's start with x. If we use x, we can also transform x to the spectral domain, and we can obtain the variable that we can call kx, if you want. This is also known as the wave number. If you want to transform the function f of x to the function f hat of kx, there is a similar definition to the ones that we have already seen. So we can integrate from minus infinity to plus infinity. We can also multiply by 1 over square root of 2 pi if you want to get the same constants in the Fourier transform and its inverse. But we are not going to multiply by 1 over square root of 2 pi. So we just keep it as is. Then we have integral of f of x times e to the I k instead of the variable omega times x instead of the variable t times dx. So if you just note it here, I have a plus. This is just the usual definition. You can still get something meaningful if you put a minus sign here. So if we put a plus here, we are going to get a minus in the inverse transform, and vice versa. That's all there is to it. It's not much more meaningful than that. The inverse transform is obtained by using this formula. So we have 1 over 2 pi integral from minus infinity to plus infinity of f hat of k sub x times e to the minus I k, this was k sub x times x, and here we have d k sub x, so we are going to integrate over k sub x. It's very similar to what we have already discussed with the Fourier transform in the time domain. And something similar you can get by substituting kx with ky or kz, and instead of x, of course, you can have y and z. So you have the same exact transformation. So you can easily generalize this to a function which depends not just on one variable, but on multiple variables like x, y, z, and the variable t. So you can transform it once, you have f hat, and let's assume that you transformed the t variable, so you have x, y, z, and instead of t you get omega, and then you can transform twice, so you get f double hat or f hat hat if you want. So we are going to transform the x variable, for example, so we have f of k sub x, y, z, w, and so on and so forth. So you can get all the way up to f with 4 hats, and we transformed all those variables, so we have k sub x, k sub y, k sub z, and omega. This function here is just simply obtained by integrating 4 times from minus infinity to plus infinity the initial function f of x, y, z, and t. So I'm going to write it here. So this is the third integral, then we have a fourth integral. These 4 integrals could be simply replaced by integral over r fourth. So let's zoom out a little bit to view it properly. Here we have f of x, y, z, and t. And here we just have the multiplication of 4 complex exponentials. So when we multiply 4 complex exponentials, we just simply add their arguments. So we have e to the minus I omega t. And then we can factor out a minus I and get minus k sub x times x, minus k sub y times y, and minus k sub z times z. We also have to multiply this expression by dx, dy, dz, and dt. So in physics, or even in mathematics, more often than not, you see some more concise notation to denote this kind of clumsy expression. So instead of having these 4 differentials multiplied together, you just have something like d4x. This is just a notation, so bear in mind that. And instead of having f of x, y, z, we replace it by just hex here. So where this x is a 4 vector, this 4 vector is usually defined like this. So we have t, x, y, and z. In physics you may get here the speed of light. I'm not going to write it here, so I'm just going to erase it. Even in physics sometimes you just simply set the speed of light equal to 1, so you can get rid of that. And instead of writing kx, ky, kz, and omega, you have the 4 vector k, which is defined as omega, kx, ky, kz, where sometimes you get the speed of light here, so you have omega over c, but I'm not going to write it. These three things here, kx, ky, kz, are also grouped together in the three vector k arrow, whereas x, y, z are usually grouped together in the x arrow. So this is a three vector x arrow. So you can more compactly write down a similar expression by using this notation. The Fourier transform of f of x, where x is a 4 vector, is given by, so in principle I should put 4 hats here, but I'm just going to write 1. We are going to write f of k, where k is a 4 vector. So this f hat here is the same as f hat that we used earlier, but I'm just going to use 1. And f hat of k is simply equal to integral over r4 of f of x, and then we have e to the I k dot x. So I have a dot product in 4 dimensions that I'm going to write out in a moment, and this I have to multiply by d4x. So what is k dot x? K dot x is the dot product of the 4 vector k with the 4 vector x. This must give us omega t minus k 3 vector dot x, and of course this is simply equal to kx times x plus ky times y plus kz times z. This is just a definition. If you know something about relativity and tensors, what this means is just k alpha times era alpha beta times k beta. So you have to sum over these two indices, alpha and beta, where alpha and beta range from 0 to 3. So we have 0, 1, 2, 3 as possible values. And era alpha beta is just a diagonal matrix, so it's the Lorentz metric, where we have 1 minus 1 minus 1. It's a 4 by 4 matrix where we have zeros of the diagonal and only ones or minus ones on the diagonal, something like this. And you simply multiply, and what you get is just this expression right here if you do this matrix multiplication. So this is a more concise notation, and sometimes you can have functions that depend not on x, y, z and t, but just on the spatial variables. So you can even have f of x, y, z, and you transform it into f of k. In this case, this is a 3 vector represented by kx, ky, and kz, whereas this is the 3 vector x. So f hat of k is just equal to the integral over r3 of d3x. So this is dx, dy, dz, and then I have f of x times e to the I k dot x. And the inverse of this is just f of x equal to, so since we have 3 transformations here, we have to divide by 2 pi to the 3rd power, integrate over r3 as well here, d3k times f hat of k e to the minus I k dot x. Whereas here, in 4 dimensions, the inverse transform would be, as you can guess, f of x is 1 over 2 pi to the 4th power, because we transform 4 times, integrate over r4 f hat of k e to the minus I k dot x d4k. And this is something that we are going to use when we are going to discuss the solution to partial differential equations. As we will see, we are going to use the transformations in a 3-dimensional space. So we are not going to do a 4-dimensional transformation. We are going to stick to the 3-dimensional case, because we are going to consider functions that only depend on space. So x, y, z. So this is what we are going to do next.